Welcome back to our final lecture on chemical kinetics. In lecture 1, we started at the molecular level and asked why reactions occur at different rates. We talked about collisions, activation energy, mechanisms, and catalysts. In lecture 2, we moved from that molecular picture to measurements. We learned how to calculate reaction rates and how rates describe the relationship between concentration and reaction rate. Now we're going to take one more step. Instead of asking simply how fast is the reaction happening, now we're going to ask how does the concentration of a reactant change as time passes? That's where integrated rate laws come in. We'll also look at half-life and then finish by returning to something we introduced all the way back in lecture 1, the effect of temperature and activation energy on reaction rates. There are several learning objectives here, but they fit into 3 main categories. First, can we predict how much reactant will remain after a certain amount of time? That's integrated rate laws. Second, can concentration versus time data tell us something about the reaction order? And third, how do temperature and activation energy affect the rate constant? That's where the Arrhenius equation comes in. So the overall goal of this lecture is to use kinetic data to predict how concentration and reaction rate change with time and temperature. As in the earlier lectures, you'll have several places where I ask you to pause and work problems in active. Please use those pauses. This lecture has quite a few equations, and they're much easier to learn when you practice each one immediately. So let's start by remembering what our rate law from lecture 2 actually told us. A general rate law might look something like this, where the rate of a reaction is equal to K, the rate constant, times the concentration of A raised to the M power, times the concentration of B raised to the N power. That equation answers the question, how does concentration affect the reaction rate at a particular moment? But imagine you're running an experiment and you want to answer something different. Maybe you want to know how much reactant will still be present after 30 seconds, or how long will it take for the concentration to fall to a particular value, or perhaps you've collected concentration versus time data and you want to use those data to determine reaction order. A regular rate law doesn't directly answer those questions. For those, we need an integrated rate law. This distinction is important. The rate law, or differential rate law, describes how the rate depends on concentration. For example, the rate of the reaction could be equal to K, the rate constant, times the concentration of A. The integrated rate law, however, describes how the concentration itself changes with time. So for a first order reaction, for example, the integrated rate law is the natural log of the concentration of A at a particular time equal to negative time rate constant at time t plus the natural log of the initial concentration of A. So here's the shorthand I want you to remember. Rate laws tell us how fast. Integrated rate laws tell us how much is left after a certain amount of time t. They're related, but they answer different questions. We're going to focus on the same 3 reaction orders we've already discussed because they're our most common. 0 order, first order, and second order. Each reaction order has its own rate law, its own integrated rate law, and its own characteristic concentration versus time behavior. Looking at the figure below here, notice that the concentration curves don't all have the same shape. A 0 order reaction loses concentration linearly with time. First and second order reactions both curve as concentration decreases, but they do so differently. Rather than trying to memorize 3 random equations, we're going to look for the pattern that we see in each. What's the rate law? What's the integrated rate law? And what kind of graph becomes linear? Let's begin with the simplest mathematical case, 0 order. For a 0 order reaction, the rate is simply equal to the rate constant. Notice there is no concentration term here. That means that the rate does not depend on the concentration of the reactant. The integrated form then is the concentration of A at time t is equal to negative KT plus the initial concentration of A. Here, the initial concentration of, or A naught, is our initial concentration. A sub t is the concentration at some later time, K is our rate constant, and T is the elapsed time. Now look at the form of this equation. It should look similar to y equals mx plus b. So when we plot the concentration of A on the y-axis and time on the x-axis, we should get a straight line with a slope of negative k if the reaction is zero order. So again, for a zero order reaction, a plot of concentration versus time is linear, and that slope is the equivalent of negative k, or the rate constant. So let's use that equation. Suppose we have a reaction A yields B, and we've experimentally determined that it is zero order. If we begin with 0.8 molar A and a rate constant that is 0.02 molar per second, the question might be how much A remains after 15 seconds. First, you want to identify the appropriate integrated rate law and define your variables. The rate law for a zero order reaction is going to be A sub t is equal to negative kt plus A sub naught, where A sub t is our unknown. That's what we're solving for. A sub naught is going to be equal to 0.8 molar, T is equal to 15 seconds, and K is equal to 0.020 molar per second. Again, this is all data that was given to us in the question. So now what we're going to do is substitute our known variables and plug and chug that calculation to get our unknown. So A sub t is going to be equal to negative times 0.020 times 15 plus 0.80. We simplify that down, and A sub t should be equal to 0.50 molar. Notice, watch your negative sign here. The negative kt is there because the reactant concentration is decreasing over time. Now let's look at first order reactions. For a reaction that is first order in A, the rate is going to be equal to K times the concentration of A. The integrated rate law then becomes the natural log of the concentration of A at time t is going to be equal to negative kt plus the natural log of A naught. You may also see this written as the ln of AT over A naught is equal to negative kt. These are mathematically equivalent forms of the equation. Again, let's ask what produces a straight line. Here, if we plot the natural log of A versus time, we should get a straight line with the slope of negative k. Notice something important in the graphs here. The actual concentration of A versus time would be curved because it's not zero order, it's actually a first order reaction. It only becomes linear once we transform according to the integrated rate law for first order reactions. So once we transform the concentration by taking its natural log, that graph will become linear. So again, for first order reactions, the natural log of A versus time would give us a linear line. So let's work an example. Suppose now our reaction of A converting to B is now first order. We begin with 0.5 molar A, and the rate constant is given to us as 0.0350 inverse seconds. So the question is how much A remains after 20 seconds? Again, we're going to do sort of the same steps that we did first. We're going to identify which integrated rate law we need and the variables that we need. So in this case, because it's first order, we're going to use the natural log of AT is equal to negative KT plus the natural log of A naught. AT is the variable that we're solving for. A naught is 0.50 molar. T is equal to 20 seconds, and K is equal to 0.0350 inverse seconds. Again, all of that data was given to us in the question. The next thing we're going to do is plug in those known variables and solve for our unknown. So here, ln of AT is going to be equal to negative 0.0350, don't forget that negative sign, times 20 seconds plus the ln of 0.50. Simplify the right side of the equation, and we end up with the natural log of AT is equal to negative 1.393. Now, in order to get rid of that natural log, we have to do e to the x on the right side. That is the inverse of ln of x is e to the x. So when we do that, we get at is equal to e raised to the negative, don't forget that negative sign, 1.393, and at becomes 0.258 molar. So we have 0.258 molar of reactant A remaining after 20 seconds. So for a reaction that is second order in A, the differential rate law for second order reactions would be the rate is equal to K times the concentration of A squared. The integrated rate law for a second order reaction is equal to 1 over the concentration of AT is equal to KT plus 1 over the initial concentration of A. Notice that this looks different. This time, the quantity that gives us a straight line is when we plot 1 over the concentration of A. So for a second order reaction, a plot of 1 over A versus time should give us a linear line if the reaction is second order. Also notice, unlike 0 and first order reactions, the slope here is positive. So our slope is going to be positive K. So let's work through the same type of problem for a second order reaction. Again, suppose our reaction A through B is now second order. Our initial concentration is 0.2 molar, and our rate constant is given to us as 0.50 inverse molar inverse seconds. And we want to be able to determine what is the new concentration after 10 seconds. So again, we're going to start with the correct equation and identify the variables that we are given and the variable that we are trying to calculate. So in this case, because it's second order, we're going to use the 1 over A equation for a second order reaction. AT is going to be our unknown. That's what we're trying to solve for. We're trying to figure out how much A is left. A naught is given to us as 0.20 molar. The time lapse is 10 seconds, and K is given to us as 0.50 inverse molar inverse seconds. We're going to plug all of those known variables into our equation and solve for our unknown. So when we do that, everything on the right side should end up equaling to 10. So we're going to end up with 1 over AT is equal to 10. Do the inverse of the right side, and we should end up with AT is equal to 0.100 molar. So after 10 seconds, we will have 0.1 molar of A remaining. Again, the first step in any of these problems is not calculator work. It's identifying the reaction order so that you can identify the right integrated rate law that you need and which variables you will need where. Then we can get out our calculator. So this is a nice summary table. And it's one that I would keep handy while you're working your homework problems. So for zero order reactions, remember our differential rate law is going to be equal to the rate is equal to K. The integrated rate law says that the concentration at A at time T is going to be equal to negative KT plus the initial concentration of A. And we will get a linear plot if we plot the concentration of A versus time, and the slope from that plot is equal to negative K. For first order reactions, our differential rate law says that the rate of the reaction is equal to K times the concentration of A. The integrated rate law then is equal to the ln of the concentration at A at time T is equal to the negative KT plus the ln of the initial A concentration. In this instance, we will only get a linear plot if we plot the ln of A versus T, and our slope is negative K. For second order reactions, the differential rate law says that the rate of the reaction is equal to K times the concentration of A squared. Our integrated rate law says that 1 over A at time T is equal to KT plus 1 over of the initial A concentration, and we will only get a linear plot if 1 over A versus time is plotted. And then in this case, our rate constant is the positive slope. So this is a good time to pause, return to the active kinetics experiment, and complete questions 38 through 47. Again, please feel free to use the summary table that was on the previous slide and the examples we just worked as a guide. Again, for each problem, first identify your reaction order. That might be from looking at the units of K or the information that you are given in the question. Then select the appropriate integrated rate law, identify your known and unknown variables, and then solve. So pause the video here and come back when you're finished. Now let's reverse the problem. Up to this point, I've been telling you the reaction order or giving you the clue from the rate constant. And asking you to use the correct equation. But what if nobody tells you? What if you don't have the rate constant? Suppose now you collect measurements of concentration over time and you don't know whether the reaction is zero, first or second order. This is common, especially if we're dealing with new reactions that we haven't elucidated the mechanism yet. So how do we let the data tell us what the reaction order is? So again, the answer comes from all of those linear relationships that we just discussed. We can take the same concentration versus time data and transform them in each of the three different ways. The transformation that produces a straight line, therefore, then identifies the reaction order. Again, going back to that summary plot, what we would do is we would take the same experimental data, and if we wanted to test it for zero order kinetics, we would plot the concentration of A versus time directly. If it gets us a straight line, then we know it's zero order. But if it gives us a curved line, then we want to go and test it for first order. So now what we would do is we would plot the natural log of the concentration of A versus time. If that gives us a straight line, boom, we know we're first order. However, if it still gives us a curve, now we want to plot it for second order. In this case, we're going to plot the data as 1 over AT versus time and see if it gives us a straight line. So again, the plot of the data that produces the best straight line identifies our reaction order. And often the way we do this experimentally in the lab is we look at our R-squared value from the fit of the data. The R-squared that is closest to 1 is going to tell us which is our best fit. So for example, here's a nice visual way to look at it. The exact same experimental data has been plotted 3 different ways here. On the left, we're plotting A versus time, and you can see it's clearly curved. On the right, the 1 over A versus time is also curved. But if you look at the middle, when we plot the natural log of A versus time, boom, we get a straight line. Therefore, this reaction is first order. And because the slope of the first order line plot is negative K, we can also extract the rate constant, right? So this is a great way for us to experimentally determine both the reaction order for a reaction and get the rate constant. All right, so now why don't you try that for yourself? Return to active and work questions 48 and 49. Look carefully at which transform plot is linear. Pause here and come back when you've finished. Now let's introduce another way of describing how quickly a reactant can disappear. That is the half-life, or T1 half, is the time required for the concentration of a reactant to fall to 1/2 of its current value. So if we begin with 100%, after 1 half-life, we should have 50% remaining. Another half-life will have 25% remaining. Another half-life, 12.5%, and so on and so on. But here's an important question. Does every reaction take the same amount of time for successive halving, right? Is T the same for every half-life? No. That, again, is going to depend on reaction order. The familiar constant half-life behavior that you may have already seen is with radioactive decay. And radioactive decay specifically follows the characteristics of first-order processes. So let's take a look at each of those half-lives according to reaction order. So here's that comparison. For a zero-order reaction, T1 half is equal to the initial concentration of A divided by 2K. For first order, T1 half is equal to 0.693 over K. And for second order, T1 half is equal to 1 over K times the initial concentration of A. So a couple things I want you to notice. For zero order reactions, as the initial concentration of A increases, T1/2 increases. So the more reactant you have, the longer your half-life is. For first order reactions, notice there is actually no correlation. T1/2 does not depend on the concentration of A. T1/2 is a constant for first order reactions, and it's based on its rate constant. Second order reactions say that a larger initial concentration of A means we have a smaller half-life. So as concentration increases, half-life decreases or goes faster. So let's use a real chemical example here. Let's take the reaction hydrogen peroxide, which decomposes as 2 molecules of hydrogen peroxide will decompose to produce 2 molecules of water and 1 molecule of oxygen. It is found to be first order with a rate constant that K is equal to 0.0462 inverse minutes. What is the half-life of this reaction? So because it's first order, we can use the half-life equation for first order reactions, which says T1/2 is equal to 0.693 divided by K. So the only variable we need to identify here is K, which again is given to us in the question. So K is equal to 0.0462. Now all we have to do is plug that K value in and plug and chug. So T1/2 turns out to be 15 minutes. So every 15 minutes, half of the hydrogen peroxide that was present at the beginning of that interval remains. And that's what we're going to use on the next slide. Suppose our initial hydrogen peroxide concentration is 0.8 molar. How much remains after 30 minutes? Remember, we just determined that the half-life for first order reactions for hydrogen peroxide is 15 minutes. 30 minutes is therefore 2 half-lives. So after the first 15 minutes, we're going to see that 0.8 molar is going to decay into 0.4 molar. After the second 15 minutes, we have another half-life decay where 0.4 molar is going to decay to 0.2 molar. So after 30 minutes, we will have 0.2 molar hydrogen peroxide remaining. Again, this clean repeated halving approach works best because this is a first order reaction with a constant half-life. Again, it's always going to be 15 minutes. So every 15 minutes, the concentration is going to decay by half. So for first order reactions, we can generalize this pattern as after 1 half-life, half remains. After 2 half-lives, a quarter remains. After 3, 1/8. After 4, 1/16. In general, the fraction remaining is 1/2 raised to the n power, but where n is the number of half-lives. But pay attention to the warning at the bottom of the side. The shortcut assumes every half-life has the same duration, and that's true for a first order reaction. Do not automatically use the shortcut for 0 or second order reactions. So let's stop here for questions 50 through 53. Before grabbing an equation, ask yourself, is this a straightforward first order half-life problem where I can use repeated halving, or do I need the full integrated rate law to determine how much is remaining? That decision is part of the solving the problem. So pause here and come back when you're done. So we're almost finished, but there's one important piece left. Back in lecture 1, we learned that increasing temperature generally increases the reaction rate. We explained that using collision theory and activation energy. At higher temperatures, a greater fraction of particles have enough energy to overcome the activation energy barrier. But now that we've spent so much time looking at rate laws, notice something strange. Where is temperature? There is no temperature unit in any of the rate expressions we have seen up until this point. And there is no explicit temperature term in any of our integrated rate laws either. Instead, temperature changes the actual value of K, the rate constant. That's the mathematical connection. And the relationship between temperature and activation energy and K is described by the Arrhenius equation, which says K is equal to AE raised to the negative EA divided by RT, where K is the rate constant, A is the frequency / orientation factor, E sub A is the activation energy, R is a gas constant, and T is temperature in Kelvin. So quickly some hints here. Higher T means we're going to have a larger K, which is going to give us a faster reaction. Mathematically here, higher E sub A, or energy of activation, is going to end up giving us a smaller K and a slower reaction. The Arrhenius equation can be arranged in several useful forms. If we take the natural log of the Arrhenius equation, we can get this graphical equation where the ln of K is equal to the ln of A minus E sub A over RT. Again, we can fit this to y equals mx plus b, which if we plot the ln of K over versus t, we should get a linear line, and the slope is then going to be equal to EA over R, which means experimental temperature and rate constant data can be used to determine the energy of activation. There's also a two-temperature version of the equation in which ln of K1 over K2 is equal to E sub A over R times the difference between 1 over T2 minus 1 over T1. This form we're actually going to use in our next calculation example. But one important reminder: temperature must always be in units of Kelvin, and energy of activation is typically going to be in units of joules per mole, because R, which is our gas constant, is given to us in units of joules per Kelvin per mole. And that constant, R, is going to be equal to 8.314, again, units of joules over K mole. And again, this is a constant, not something you'll have to remember. I'll give that to you on the exam. So let's use our hydrogen peroxide example again. Here we're told hydrogen peroxide decomposes according to the balanced chemical equation. For every 2 molecules of hydrogen peroxide, we get 2 molecules of water and 1 molecule of oxygen. At 25 degrees Celsius, the reaction has a rate constant of K1 is equal to 2.5 times 10 to the minus 3 inverse seconds, and an activation energy for the reaction is 50.0 kilojoules per mole. If a chemist warms the reaction mixture to 45 degrees Celsius, what is the new rate constant? So the first thing we want to do is identify the form of the Arrhenius equation that we need and the known and unknown variables. So here we're asked to determine a new rate constant with result to a change in temperature. So we're going to use the mathematical relationship that has 2 temperature terms and 2 rate constant terms. So that's going to be the ln of K2 over K1 is equal to negative E sub A over R times the difference between 1 over T2 minus 1 over T1. We also need to identify which variable it is we're solving for and identify all of our known variables given to us in the equation. So K1 is given to us as 2.5 times 10 to the minus 3. K2 is the unknown. That's what we're trying to solve for. The energy of activation is given us as 50.0 kilojoules per mole, but remember, we're dealing with this R constant, which is in units of joules, so we need to convert the energy of activation from kilojoules to joules by multiplying by 1,000, so 50,000 joules per mole. T1 is given to us as 25 degrees Celsius and T2 is given to us as 45. Again, we need to go ahead and convert that to Kelvin so that we're in agreement with our constant R. So for 25 degrees Celsius, that would be 298 Kelvin, and for 45 degrees Celsius, that would be 318 Kelvin. Once we've identified all of those unknown and known variables, we can then plug them into our equation and solve for our unknown. So as you can see, we've done that here. So the ln of K2 over K1, which is 2.5 times 10 to the minus 3 inverse seconds, is equal to the energy of activation over that R constant times 1 over T2 minus 1 over T1. If we simplify the right side of that equation, we should get 1.27 is equal to ln of K2 over 2.5 times 10 to the minus 3. Again, to get rid of this natural log, we need to do the inverse, which would be e to the negative number. So there really should be a negative, e to the number. Again, this is going to end up negative, so that's why that negative sign goes away. Negative times a negative is a positive. So we'll end up with e to the 1.27 is equal to this expression here. Now all we have to do is, again, rearrange and simplify, and eventually you should get K2 is equal to 8.9 times 10 to the minus 3 inverse seconds. But before you look at the number itself, ask yourself, does this answer make physical sense? We raise the temperature, and we know as temperature increases, the rate constant should increase. So remember, our original rate constant was 2.5 times 10 to the minus 3. Our new rate constant is 8.9 times 10 to the minus 3. So this is bigger than K1. That makes sense. Okay, so the new rate constant is roughly 3.5 times larger than the original value. So the prediction check here is a great way to catch sign errors and make sure that we sort of did our math the right way. All right, so now it's your turn. Complete questions 54 through 59 in active. For Arrhenius problems, slow down and check 3 things before calculating. 1, are your temperature units in Kelvin? 2, is activation energy in units consistent with R, typically having to convert kilojoules to joules? And 3, does your final answer make physical sense, right? If your temperature is increasing, your rate should increase. If your temperature decreases, K should decrease. And then when you've completed these questions, you've finished the kinetics homework set. Good job. All right, so let's finish by connecting all 3 lectures. On the left side of this diagram, we start with the reaction mechanism. The molecular pathway influences the experimentally observed rate law. The rate law then tells us the reaction order. And once we know the reaction order, we know which integrated rate law applies. And that integrated rate law allows us to predict concentration as a function of time. Now look at the right side. Here, the temperature and activation energy are related to the rate constant through the Arrhenius equation. That value of K then helps determine the reaction rate. These aren't separate pieces of kinetics. They're different ways of describing the same reactant system. One side helps us describe how concentration changes, and the other helps us understand why the speed of that change depends on energy and temperature. Together, they give us a more unified picture of chemical kinetics. So here's the entire kinetics unit in a few statements. Kinetics connects what molecules are doing to what we measure experimentally. Collision theory explains why some molecular encounters lead to reaction and others do not. Rate laws describe how concentration affects reaction rate. Integrated rate laws let us predict how concentration changes over time. Half-life gives us a characteristic timescale for reactant disappearance. And the Arrhenius equation connects temperature and activation energy to the rate constant. And catalysts provide an alternative, lower activation energy pathway, which increases K and therefore increases the reaction rate. So if you find yourself getting lost in all of the equations, return to the questions each equation answers. Why does the reaction occur at this rate? How does concentration affect the rate? How much reactant will remain after a certain amount of time? And how will changing temperature or the energy barrier change the reaction? Those are the core ideas of kinetics. Make sure you've completed the active assignment and bring your questions with you to class if you're meeting in person, or post them on the Muddiest Point discussion board if you're learning online. Our in-class activity will give us a chance to put these different pieces together rather than treating them as isolated equations. All right? Until then, I'll see y'all next time. Bye.